All right, guys, we'll continue on with our opening chapter in Pre-Calc Advanced, all about functions, with section 2.3. In section 2.3, we really talk about the graph of a function and the properties of those graphs. Okay, so we begin our section 2.3 notes with the terminology of increasing and decreasing. Okay, when would a function be increasing? When would it be decreasing? How do we write it, etc. So, a function is said to be increasing if, or decreasing if, as x gets larger, f of x gets larger. Okay, now when we're thinking about as x gets larger, okay, we'll talk about what that might look like on a graph. Same thing with decreasing. As x gets larger, f of x, or the y value, gets smaller. All right. Now, as x gets larger, and this is a thought about how we read a graph in mathematics, really what we want to be thinking is from left to right. Okay? That's how x gets larger. Okay? So when we're thinking of increasing and decreasing intervals, we really want to read the graph from left to right. I'm going to start all the way on the left. We're going to see, all right, is it increasing or decreasing to what point? Then has it changed? Is it now increasing or decreasing? And then we go all the way to the right of the graph. So I'm going to draw just a plane here, and all right, and I'm going to use two colors here to kind of show you guys increasing and decreasing. All right, we'll make this a little bit more shaded purple here. Okay. The red, in red here, okay, if we're reading from left to right, I start here. Okay, this first red portion of this curve, all right, as x is getting larger, or as we're moving from left to right, this function is increasing. The y's are getting larger. So this interval would be an interval of increase. And then, starting right here, we'll talk about, we call this a maximum point, and we'll talk about that as we get going in these notes. From here, this point, this x value, going from left to right, this would be an interval of decrease. And then this final portion would be, again, an interval of increase, looking from left to right. All right. Now, how are we going to write this? Okay. We want to use x values to state the intervals. All right, now I'm going to put some x values on here. Let's say this x value is -2, and this x value is +3. Okay? So if I wanted to tell you where this graph was increasing and decreasing, it would be very simple. It would be increasing on the interval of -infinity. So we have an arrow here, meaning this is going to go all the way to the left, never going to stop. So from left to right, -infinity, all the way to -2. All right. Union with the next interval, or in this case, the only other interval of increase, starting at x equals 3, all the way to infinity. And then the interval of decrease here would be everything but that. From x equals -2, it is decreasing all the way until we get to x equals 3. And that would be an answer if we asked you, where is this function increasing or decreasing? Okay. We use parentheses always with intervals of increase and decrease. It should make sense to you. At this maximum point or at this minimum point, it really wouldn't make sense to determine whether the function is increasing or decreasing at that point, which is why we use the parentheses to almost not include that x value. And then in theory, your book and other, textbooks in the mathematical world, it doesn't really matter. You might see brackets here. At Highland Park, we prefer using in parentheses with our intervals of increase and decrease. Okay? All right. Let's move along to evaluating using a graph. All right, evaluating using a graph should be pretty simple here. And when we evaluate using a graph, we're going to use a piecewise function here as a little bit of a example. Okay, we'll go maybe 1, 2, 3, 4. We'll go 5 in each direction here. We'll draw a few pieces of this graph. We'll do it in red here. Didn't want that. We'll go here. All right, if that was our piecewise function here, we could just ask you similar questions to we did in section 2.1. We could say if this is f of x, let's find f of negative 1. All right, so we take a look at negative 1, the x value. We have an open circle here. We don't want that one. We have a closed circle up here at 5. The answer to f of negative 1, that would equal 5. Okay. We could ask for f of 1. F of 1 is 1, as you can see right here. X equals 1, f of x or y equals 1. All right, we could ask you, let's see, f of negative 4. Well, if we go over here to negative 4, there's only an open circle. I have no defined points at x equals negative 4. So that would be undefined. Okay. Some of the other things that you might see us ask you for some things that look like this here. Let's go. Like a little absolute value function here. We'll call this f of x. And then we'll do a little, maybe we'll do a parabola of some sort here. Okay, so not only can we evaluate one graph, we can also compare two functions. Okay. So we might ask you a question like, where, for what x values, is f of x equal to g of x? So if we think about this, for two functions to be equal, their y values would be equal, or it's just very simply where the graphs intersect. Okay? If we're asking you when the functions are equal, it would be when their points are the same, or where they intersect. In this case, at x equals negative 1, and at x equals 1. All right? We could ask you where is g of x greater than f of x. All right? Now, this should be an interval. All right? G of x greater than f of x. Well, g of x, where is g of x above f of x on this graph? Well, from negative 1 to 1. From x equals negative 1 all the way to x equals 1, g of x is above or greater than f of x. Okay? Why are we using parentheses? There's no equals to bar underneath. If there was, we'd use brackets here. We could ask you f of x is greater than g of x. Maybe we'll even do greater than or equal to g of x. Get our brackets involved here. Well, basically everywhere else. So f of x is greater than g of x from negative infinity all the way to negative 1. We're going to use a bracket with the negative 1 because we have the equals to bar underneath. And then from 1 to infinity. Okay? just some different examples of evaluating using a graph. All right, and then properties of functions, maxima and minima. That's the plural for maximum and minimum. We're really looking for local maxima and minima. All right, so local minimum. So we'll give you a graphical representation and then kind of the definition here. This point right here would be considered a local minimum. It is not the lowest point on this graph. The lowest point on this graph, as you can see, would be all the way down at negative infinity. But if I give you the definition of local minimum, it should make a lot of sense. The point at which a function goes from decreasing to increasing. Decreasing, 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 stops, turns, goes to increasing. This is your local minimum. A local maximum would be the opposite of that. Graphical representation. This right here would be a local max. The point at which a function goes from increasing to decreasing. Increasing, 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 starts to decrease. There is your local maximum. Okay? If your local maximum or minimum is truly the minimum or maximum of the function, it's called an absolute maximum or a minimum. A couple things. If we ask you where, if we use the word where, we want either the x value or the coordinates. All right, where is the local maximum? You could answer at x equals 0 or at the point 0, 3. If we ask you for the min or max value, we are looking for the y value. All right, so let's say this was at 0, 2. Just to give you the difference in terminology with the questions. If I said, where is the local maximum, you could tell me at x equals 0, or you could tell me at the point 0, 2. If I asked you, what is the maximum value at x equals 0, you would say that the maximum value is 2. All right, and that wraps up section 2.3.